How does quantum noise cause readout errors? Imagine trying to listen to a whisper in a noisy room. That's similar to what happens when measuring a quantum bit, or qubit, in a quantum computer. Quantum noise is like that background chatter that makes it hard to hear the true message. When we measure a qubit, it collapses from a quantum superposition, where it can be both 0 and 1 at the same time, into a definite classical bit, either 0 or 1. But this process isn't perfect, and noise can interfere, causing errors in what we read out. One big source of error is decoherence during measurement. Think of decoherence as the qubit losing its quantum state over time. If the measurement takes longer than the qubit's coherence time, the qubit might decay from a 1 to a 0 or vice versa while we're trying to read it. This decay can lead us to record the wrong value, making the measurement unreliable. Another factor is the overlap of signals. When measuring a qubit, we detect physical signals like microwave pulses or photon counts. These signals aren't perfectly distinct. They have fluctuations and noise. Sometimes, the signal from a qubit in state 0 can look very similar to the signal from state 1. This overlap makes it tricky for the measurement device to tell the difference, leading to misclassification. Classical noise also plays a role. Noise from the measurement equipment, such as transmission lines or amplifiers, can flip the observed bit. For example, a tiny electrical disturbance might cause what should be a 0 to appear as a 1, or the other way around. These errors are called classical bit flip errors and add to the overall measurement inaccuracies. Energy relaxation during readout, known as T1 decay, is another culprit. During the measurement pulse, the qubit might lose energy and change its state. If a qubit in the excited state relaxes to the ground state during measurement, it can cause us to record the wrong outcome. All these effects combine to make the measurement a noisy process. Instead of perfectly capturing the qubit's true state, noise introduces errors that can distort the results. This is especially problematic in quantum error correction, where detecting and fixing errors depends on accurate measurements. Since qubits cannot be copied due to the no-cloning theorem, we're relying on indirect methods like syndrome measurements to identify errors. But if the measurement itself is noisy, it becomes more challenging to distinguish real errors from measurement mistakes. To combat these issues, scientists use calibration techniques to understand how often errors happen and apply classical post-processing to correct some mistakes. Improving hardware, like shortening measurement times and using quantum-limited amplifiers, helps reduce noise. Advanced measurement protocols also aim to minimize the impact of noise during error correction cycles. In the end, reducing readout errors is vital for making quantum computers more reliable. While other errors like gate errors and decoherence matter, readout noise is a major obstacle in current quantum devices. Addressing it helps us move closer to practical, fault-tolerant quantum computing.